In Lesson 5.1, we're looking at bisectors, medians, and altitudes. You'll learn to identify and use perpendicular bisectors and angle bisectors in triangles, and identify and use medians and altitudes in triangles. How can you balance a paper triangle on a pencil point? I'm sure you've been dying to know. Acrobats and jongleurs often balance objects while performing their acts. These skilled artists need to find the center of gravity for each object or body position in order to keep balanced. The center of gravity for any triangle can be found by drawing the medians of a triangle and locating the point where they intersect. This lesson has lots and lots of vocabulary. A perpendicular bisector of a side of a triangle is a line, segment, or ray that passes through the midpoint of the side and is perpendicular to that side. Perpendicular bisectors of segments have some special properties. Theorem 5.1 says, any point on the perpendicular bisector of a segment is equidistant from the endpoints of the segment. For example, if segment AB is perpendicular to segment CD and segment AB bisects segment CD, then AC is equal in length to AD and BC is equal in length to BD. And Theorem 5.2, any point equidistant from the endpoints of a segment lies on the perpendicular bisector of the segment. So if AC equals AD, then A must lie on the perpendicular bisector of segment CD, and if BC equals BD, then B must lie on the perpendicular bisector of segment CD. Since a triangle has three sides, there are three perpendicular bisectors in a triangle. The perpendicular bisectors of a triangle intersect at a common point. When three or more lines intersect at a common point, the lines are called concurrent lines, and their point of intersection is called the point of concurrency. The point of concurrency of the perpendicular bisectors of a triangle is called the circumcenter. Theorem 5.3 is a circumcenter theorem. It states the circumcenter of a triangle is equidistant from the vertices of a triangle. So if J is the circumcenter of triangle ABC, then AG is equal in length to BJ is equal in length to CJ. A locus is the set of all points that satisfy a given condition. The perpendicular bisector can be described as a locus of points in a plane that are equidistant from the endpoints of a given segment. An angle bisector can be described as a locus of points in a plane equidistant from the sides of an angle. Since the sides of an angle are contained in intersecting lines, the locus in a plane equidistant from two intersecting lines is the angle bisector of the vertical angles formed by the lines. Theorem 5.4 says any point on an angle bisector is equidistant from the sides of an angle, and any point equidistant from the sides of the angle lies on the angle bisector, the converse. As with perpendicular bisectors, there are three angle bisectors in any triangle. The angle bisectors of a triangle are concurrent, and their point of concurrency is called the incenter of a triangle. Theorem 5.6 is the incenter theorem. It says the incenter of a triangle is equidistant from each side of the triangle. So, for example, if K is the in-center of triangle ABC, then KP is equal in length to KQ is equal in length to KR. A median is a segment whose endpoints are a vertex of a triangle and the midpoint of the side opposite the vertex. Every triangle has 3 medians. The medians of a triangle also intersect at a common point. The point of concurrency for the medians of a triangle is called a centroid. The centroid is the point of balance for any triangle. Theorem 5.7 restates that the centroid of a triangle is located 2/3 of the distance from a vertex to the midpoint of the side opposite the vertex on a median. So for example, if L is on the centroid of triangle ABC, then AL is 2/3 of AE. BL is 2/3 of BF, and CL is 2/3 of CD. Example 2, I skipped one because it was a proof, and we're going to let those go this chapter. Points U, V, and W are the midpoints of YZ, ZX, and XY, respectively. Find A, B, and C. Well, we're looking at the point where the medians cross, so that'll be the centroid, and so we have that whole 2/3 relationship going on. So let's go in alphabetical order and start with A. So the long part here, so that's 7.4, is 2/3 the length of the whole thing. So 2/3 of the length of YV would be 7.4 plus 2A. I know fractions are our friends, but I think let's go ahead and multiply both sides by 3/2 right away to get rid of the fraction. Goodbye. So the 2/3 and 3/2 cancel out, and 3/2 or 1.5 times 7.4 is 1.1. That's not so bad. Equals 7.4 plus 2A. So we're going to subtract 7.4 from both sides of the equation. So we have 3.7 is 2A divided by 2. And A is going to equal, okay, so A is 1.85. Guess what? We still need to keep going and find B and C. So looking at B, 3B plus 2 is our 2/3 this time. So 3B plus 2 is 2/3 of the whole length. So the whole length of XU would be 3B plus 2 plus 8.7 would be 10.7. And again, let's get rid of the 2/3, so multiply both sides by 3/2. Goodbye. So I've got 4.5B plus 3 equals 3B plus 10.7, writing it by the problem. Subtract 3B from both sides of the equation. So 1.5B plus 3 is 10.7. Subtract 3 from both sides of the equation. And I cheated for space there. I've got 1.5B, sorry, my decimal's ugly, equals 7.7. Divide both sides by 1.5. And I have B is about, if I round to the nearest hundredth, 5.13. Now for C, 15.2 is the 2/3. So again, let's multiply both sides by 3/2 to get rid of that. So 15.2 times 1.5 is 22.8 equals 5C plus 15.2. I'm going to subtract 15.2 from both sides of the equation. So I have 5c equals, so we've got 5c equals 7.6, divide both sides by 5, and c is 1.52. An altitude of a triangle is a segment from the vertex to the line containing the opposite side and perpendicular to the line containing that side. Every triangle has, you guessed it, 3 altitudes. The intersection point of the altitudes of a triangle is called the orthocenter. Okay, now all of that to say that the problems that I'm going to assign from the book are going to look more like this. In triangle RST, RU is an altitude. Okay, what's an altitude? It is perpendicular. And they ask us to find y if the measure of RUS, that's 90, equals 7y plus 27. So we know that equals 90. So if we subtract 27 from both sides of the equation, 7y will equal 63, which conveniently divides by 7 very well. So y is 9. Okay, in the directions it also said that SV was a median, so that means that V is the midpoint of RT. And they said find RV if RV equals 6a plus 3 and RT is the whole thing, equals 10a plus 14. So I could have 6a plus 3 equal to half of that. So that would be 5a plus 7. Subtract 5a from both sides of the equation. So we have a plus 3 equals 7. Subtract 3. And a equals 4. Oh, but wait, they said to find RV, so we need to substitute that back in. So 6 times 4 is 24, plus 3, RV would be 27. Okay. Which congruent statement is true if P is the circumcenter of triangle WXY? Okay, the circumcenter is the intersection or point of concurrency of the perpendicular bisectors. So let's draw those in. So the circumcenter is the intersection of the perpendicular bisectors. So that looks like about the middle. And that would be perpendicular. That's about the middle. Perpendicular. And perpendicular. Hopefully. I'm eyeballing it. And we know that from theorem 5.3, the circumcenter is equidistant from the vertices of the triangle. So if our circumcenter, they called it point P, we could connect that to the vertices of the triangle, and those should all be the same. So WP should be congruent to XP is congruent to PY. So that would be that choice. Okay, so here's all of our vocabulary summed up in one chart. When the perpendicular bisectors cross, the point of concurrency is called the circumcenter. The angle bisectors cross at the incenter, the medians cross at the centroid, and the altitudes cross at the orthocenter.